Hello and welcome to third session of Computational Fluid Dynamics by Mr. CFD team. In this session, we are going to become familiar with solvers of Fluent software and pressure-based method of pressure and velocity coupling. Transport equations for each velocity component, momentum equations, can be derived from the general transport equation by replacing the variable phi by u, v, and w respectively. Every velocity component appears in each momentum equation, and the velocity field must also satisfy the continuity equation. This can be clearly shown by considering the equations governing a two-dimensional laminar steady flow. The pressure gradient term, which forms the main momentum source term in most flows of engineering importance, has been written separately to facilitate the discussion that follows. The solution of equation set presents us with two new problems. The convective terms of the momentum equations contain nonlinear quantities. For example, the first term of equation is the x derivative of ρu2. All three equations are intricately coupled because every velocity component appears in each momentum equation and in the continuity equation. The most complex issue to resolve is the role played by the pressure. It appears in both momentum equations, but there is evidently no transport or other equation for the pressure. If the pressure gradient is known, the process of obtaining discretized equations for velocities from the momentum equations is exactly the same as that for any other scalar. In general-purpose flow computations, we also wish to calculate the pressure field as part of the solution, so its gradient is not normally known beforehand. Coupling between pressure and velocity introduces a constraint in the solution of the flow field. If the correct pressure field is applied in the momentum equations, the resulting velocity field should satisfy continuity. Both the problems associated with the nonlinearities in the equation set and the pressure-velocity linkage can be resolved by adopting an iterative solution strategy such as the simple algorithm. By solving the velocities and pressure field, other equations can easily discretize, because by knowing these parameters, other equations will decouple. There are several methods for solving continuity and momentum equations, and here we are going to find the formulation of different methods that Fluent use. We can choose between two overall solver type in Fluent, pressure-based and density-based. Historically, the pressure-based approach was developed for low-speed incompressible flows, while the density-based approach was mainly used for high-speed compressible flows. However, recently both methods have been extended and reformulated to solve and operate for a wide range of flow conditions beyond their traditional or original intent. In both methods, the velocity field is obtained from the momentum equations. In the density-based approach, the continuity equation is used to obtain the density field, while the pressure field is determined from the equation of state. On the other hand, in the pressure-based approach, the pressure field is extracted by solving a pressure equation or pressure correction equation, which is obtained by manipulating continuity and momentum equations. Using either method, ANSYS Fluent will solve the governing integral equations for the conservation of mass and momentum, and when appropriate, for energy and other scalars such as turbulence and chemical species. In both cases, a control volume-based technique is used that consists of division of the domain into discrete control volumes using a computational grid, integration of the governing equations on the individual control volumes to construct algebraic equations for the discrete dependent variables, unknowns such as velocities, pressure, temperature, and conserved scalars, linearization of the discretized equations and solution of the resultant linear equation system to yield updated values of the dependent variables. The two numerical methods employ a similar discretization process, finite volume, but the approach used to linearize and solve the discretized equations is different. In this session, we will address the pressure-based solver and the different methods that Fluent uses for solving pressure-velocity coupling. There are four choices for the pressure-velocity coupling: simple, simple C, PISO, and coupled. The segregated methods, simple, simple C, and PISO, imply that pressure and each of the velocity equations are decoupled from each other and solved independently. In contrast, the coupled method handles all four equations of x, y, and z momentum, along with the continuity equation, simultaneously. In the methods for pressure-velocity coupling of pressure-based solver, as mentioned earlier, the pressure variable is calculated by solving the pressure equation or pressure correction equations derived from the continuity equation. The pressure-based solver employs an algorithm which belongs to a general class of methods called the projection method. Two pressure-based solver algorithms are available in ANSYS Fluent: a segregated algorithm and a coupled algorithm. The segregated algorithm solves the governing equations, momentum, pressure, energy, etc., sequentially. It traditionally uses an iterative approach, such as the simple, semi-implicit method for pressure-linked equations algorithm, to resolve the coupling between velocities and pressure. Segregated algorithms follow these steps. 1. Solve the momentum equations to update velocity fields. 2. Use the continuity equation to update the pressure field, typically through a pressure correction approach like SIMPLE. 3. Correct the velocity field using the updated pressure. 4. Solve other scalar transport equations, e.g., energy, turbulence, based on the updated flow field. 5. Repeat this loop till solution convergency. Segregated algorithm requires less memory than the coupled method because each equation is solved separately and it is well suited for incompressible and mildly compressible flows. But, potentially, it has slower convergency due to the sequential nature of solving equations and may require more iterations to reach a converged solution, especially for complex flows with strong coupling between velocity and pressure. The coupled algorithm solves the momentum and pressure equations simultaneously rather than sequentially. This approach typically employs a fully coupled approach, where the algebraic systems resulting from the discretization of these equations are solved together. Coupled algorithm follow these steps. 1. Formulate a single system of equations for pressure and velocity. 2. Solve this system directly or iteratively to update both velocity and pressure fields. 3. Solve other transport equations as necessary. Coupled algorithm has faster convergency compared to the segregated method, especially for complex flows with strong pressure-velocity interactions. Also, it can handle a wider range of flow regimes, including highly compressible and transient problems effectively. But this algorithm requires higher memory, as the systems of equations tend to be larger. Now let's follow the mathematical formulation of each pressure-velocity coupling method in detail. The first one is simple. For x momentum equation, we can start from the integral form. Convection term, diffusion and source term of pressure, and volumetric source term. If we use the same nomenclature for the nodes of mesh, var delta, that delta is delta x and y that assumed to be equal, u at the east face in the power of 2 minus u at the west term in the power of 2, plus uv at the north node minus uv in the south term. And we can discretize in a central manner as we have done previously. Value of property at face is the average of values at neighborhood cells. The second term, or diffusion, can be discretized in central manner as we saw in session 2. Third term, that is the pressure source term, we can discretize in central manner too. that we pressure at the east node minus pressure at the west node divided by 2 delta x. To generalize, we can number the cells in the x direction with the index I, in the y direction with the index j, and in 3D simulations, the z direction with the index k. General format of x momentum will be in this form that uij can be found with the value u and v in the neighborhood cells. Coefficients of ANI and ANJ can be found based on schemes that we used for discretizing velocities and pressure. For example, we find these coefficients in the last session for a 2D geometry with the central scheme for each cell. The delta y will be placed with A, or area of the face, in 3D simulations. For solving this relation, because we have 3 unknown u, v, and pressure, we start with a pressure guess and the velocity guess. We can find the velocity at the I and j at the next iteration. This plus means next iteration. The actual pressure will be the assumed pressure plus a deviation pressure. Also, for the x velocity and y velocity, actual velocities are the assumed velocity plus a deviation velocity. If we substitute the actual velocity in the formulation, we can write this relation. And by differencing these two equations of 1 and 2, we can find a relation for the division parameters. In this relation, for the simple method of pressure and velocity coupling, sigma of u prime and v primes are assumed to be 0. And it's not a bad assumption because after reach convergency, the division of solution from the actual velocities is 0. So after convergency, this relation doesn't have error, and we can find the u prime as a function of p primes. So let's see what we found. We found a relation for the momentum equation that we can find the velocity at the next equation based on the assumed pressure and velocities. Also, we find a relation that the division of velocity can be calculated based on the pressure deviation for simple algorithm. By replacing the velocity in the continuity equation, we can derive a pressure correction equation. By convert the equation into integral form and integrate over the faces of control volume, we can derive this equation. And also, we can use this relation that velocity is equal to assumed velocity plus the deviation velocity. And we can replace the division velocity with the pressure deviation, based on this formulation that presented in above. So these three equations can be combined. U star plus coefficient d times pressure's division at the cell I-1 and j minus pressure deviation at I and j at the east faced, and so on for the rest of equation. Now we can discretize this equation. For example, U star at east face can be replaced with the average of U star at the I and j node, and U star at I plus 1 and j node. and the d coefficient at the east phase can be replaced with di plus 1 and j. Also for the east face pressure division at point ij minus I plus 1 and j node. We can continue for the rest of the equation. Let's review the simple, semi-implicit method for pressure-linked equations algorithm in summary. Initially, the momentum equations are solved based on an assumed pressure and velocity field, which are also known as the initial conditions. By substituting the velocity obtained from the momentum equation into the continuity equation, we derive the pressure correction equation and solve for the pressure deviation, denoted as P'. The initial velocity corrections at adjacent cells are assumed to be 0. In the next step, using the pressure deviation, we determine U' and V', the velocity corrections, and update the velocities and pressures using these corrections. Here, alpha represents the under-relaxation factor for velocity and pressure. If alpha is set to 1, it's highly likely that the solution will become unstable in the initial steps, as the initial pressure and velocity fields may be far from the true solution, potentially causing the solution to diverge. However, if the under-relaxation factor is set to 0, the corrections to pressure and velocities will not be applied, preventing the simulation from progressing. In the following step, once the pressure and velocity fields are updated, we solve other scalar equations, if applicable, such as those for species transport or radiation. The values obtained in each iteration replace U star, V star, and P star. This process is repeated iteratively until the velocity and pressure corrections, U', V', and P' approach 0 or meet criteria we have defined. Once these criteria are satisfied, the simulation is complete. Now, let's take a look at the simple C, semi-implicit method for pressure-linked equations consistent, algorithm for pressure-velocity coupling. If we examine the equation derived from the momentum equation by replacing velocity and pressure with the assumed values plus their corrections, we can formulate this process. In the simple algorithm, the correction velocities, U'(Ni) and V'(Nj) at the neighboring cells in the I and j directions are assumed to be 0, thereby creating a relationship between pressure and velocity corrections. However, in the simple C algorithm, we assume that the velocity corrections are constant and equal to the velocity correction at nodes I and j. With this assumption, by substituting U'Ij into the corrections at the neighboring nodes U'Ni and V'Nj, we arrive at an equation where U' can be calculated based on P'. Thus, when we define the coefficient dij, the rest of the simple algorithm operates similarly to the simple algorithm, with the only difference being the calculation of dij, resulting from the different assumption about velocity corrections. Because of this modification in assumption of velocity correction calculations, simple C algorithm can converge faster than simple algorithm, especially beneficial in larger or more complex simulations, where the improved velocity-pressure coupling reduces the number of iterations needed to reach a converged solution. The PISO, pressure implicit with splitting of operators, algorithm involves one predictor step and two corrector steps and can be seen as an extension of the simple algorithm, with an additional corrector step to enhance convergence and stability. Similar to the simple algorithm, PISO begins by using an assumed velocity and pressure to solve for the velocity in the next iteration. Next, by substituting the velocity back into the continuity equation, a pressure correction is calculated, allowing for the correction of both velocity and pressure. However, in PSO, an additional correction is applied, resulting in twice corrected pressure and velocities, denoted as P triple prime, U triple prime, and V triple prime. This additional correction step improves the accuracy and stability of the solution. To find the second correction of pressure, replace the corrected and twice corrected pressures and velocities in the momentum equation. The velocities inside the summation are from one step earlier. By differencing the two equations of x momentum, we can derive this relationship. P double prime is defined as the twice corrected pressure minus the corrected pressure. Additionally, the corrected velocity minus the assumed velocity gives U prime and V prime. By rearranging the equation to calculate the twice corrected velocity, we derive another equation. These parameters are known from the previous step, allowing us to establish a relationship between the twice corrected velocity and the pressure double prime. By substituting this relation into the continuity equation, we can solve for P double prime. Consider the continuity equation for a steady state in integral form, representing a balance of mass flux across the control volume walls. For further simplification, assume constant density and uniform grids. Using a central discretization scheme, we can approximate the velocity at cell faces by averaging the velocities at neighboring grid points. The velocity at grid point P cancels out, and we can input the twice corrected velocity. The twice corrected velocity can be substituted using the relation based on double prime. Leaving the resulting equation with only P double prime as the unknown. Assuming initial P double prime values to be 0, we can iteratively solve for P double prime at each cell. Finally, P triple star is calculated as P double star plus P double prime, which is equivalent to P star plus P prime plus P double prime. The twice-corrected velocities u and v can also be determined. Now let's review the PISO algorithm for pressure-velocity coupling. Initially, we assume an initial pressure and velocity, which allows us to calculate the velocity u star for the next iteration. Then, we calculate the pressure correction. Afterward, we compute the corrected velocity and pressure. In the subsequent step, we derive the momentum equation again for the second correction. By substituting the velocities back into the continuity equation, we find the twice-corrected pressure. We then update the velocities for the twice-corrected pressure and velocities. After that, we solve any other scalar transport equations. This loop is repeated until convergence is achieved. In a coupled algorithm, unlike segregated algorithms where each equation is decoupled from the system and solved individually, all equations are solved simultaneously in a coupled system, allowing us to find the x, y, and z velocities, as well as pressure, together. In the coupled algorithm, for the x momentum equation, only the u or x velocity is active, while the other velocities, v and w, in 3D simulations, are imported from the previous iteration. In the y momentum equation, the only active variable is the y velocity, and in the z momentum equation, only w z velocity is active. For example, if we have 4 cells in our domain, by discretizing the velocities and pressures in the x momentum equation, where the only active variable is the x velocity, we obtain a set of equations. After discretization, depending on the schemes used for discretizing velocities and pressure, we have B11 equal to a coefficient times the x velocities at each grid point, such as A11U1 plus A12U2 plus A13U3 plus A14U4. Similarly, by discretizing the pressures, we can add terms like D1 to 1P1 and apply this to all nodes. We will have 4 x momentum equations, one equation for each cell. For the y momentum equation, only the y velocity is the active variable, meaning we have only v and p variables appearing in the rearranged equation. In the continuity equation, all velocities are active, and there is no pressure in this formulation, leading to an expression like E11U1 plus E1 top 2U2 plus E13U3 plus E14U4 plus F11V1, continuing this pattern to the last node. If we arrange the equations into a matrix form, each row of the coefficient matrix is multiplied by the column of unknowns to solve the left-hand side of the equation in the results matrix. For the first row, we have coefficients like A11, A12, A13, A14 for the x velocities, zeros for the coefficients of y velocities, and D11 to D1.4 for the coefficients of pressure at each node. The matrix of unknowns would consist of U1, U2, U3, U4, V1, V2, V3, V4, and P1, P2, P3, P4. Constants from each equation are moved to the other side of the equation and are written in the results matrix. To complete this setup for the coefficient matrix, we have a set of zeros for the y-velocity coefficients in the x-momentum equations and 4 rows and columns for the pressure coefficients in the x-momentum equation. When dividing the matrix into 4 by 4 sets of coefficients, we have zeros for the x-velocity coefficients in the y-momentum equations. For the continuity equation, there are coefficients E and F, with zeros for the pressure coefficients. If we draw the diagonal of the coefficient matrix, we notice zeros on the diagonal. Although this system is solvable, having zeros on the diagonal is not preferable. Therefore, we aim to set the equations in a different form to address this issue. Consider the x-momentum equation. For the x-momentum equation, if we solve for uij after discretizing using different schemes that we choose, it becomes a summation of x velocities at the neighboring cells minus the pressure gradient at node ij plus a constant. This constant arises from the other velocity parameters, v, and in 3D simulations, w. In the x-momentum equation, these variables are considered input from the previous iteration and thus remain constant. By dividing the equation by aij, this form can be achieved. Similarly, for Vij, using the v-momentum equation, we derive a similar relation. By substituting equations 1 and 2 into the continuity equation, we find that x velocities, pressure, y velocity, and also some constants in the formulation of the continuity equation. Thus, the continuity equation includes terms like E11U1 to E14U4, F11V1 to F14V4, and D31P1 to D34P4, with the right-hand side equating to a constant result denoted as B31. So, for a complete 3D simulation, this would be the matrix of equations that must be solved. Here, the lowercase n represents the number of cells in the domain. We can see that the coefficients of x velocity a, y velocity b, and z velocity c are present as sets of n by n coefficients. The variables u, v, w, and pressure are determined simultaneously. Our results for velocities and pressure will satisfy the 3 momentum equations as well as the continuity equation, ensuring consistency across the simulation. Coupled algorithms solve all governing equations simultaneously as a single system. This approach is generally more complex due to the need to handle a larger matrix of variables. So this algorithm has higher computational cost in each iteration and requires more memory. But it offers faster convergence and enhanced stability, particularly beneficial for problems with strong interdependencies among variables, such as compressible flows or highly interacting multiphysics systems. In this session, we learned about the different types of pressure-velocity coupling solutions in pressure-based methods. At this point, you should be familiar with the different methods of coupling pressure and velocity, including simple, simple C, PISO, and coupled. Additionally, you should understand why the coupled method is more accurate and requires smaller iterations to converge, but also needs more memory than segregated methods. Furthermore, we discussed how the PISO method, with additional corrections in pressure and velocities, can produce more accurate results for transient simulations rather than other segregated methods. In upcoming sessions, we will explore density-based methods of pressure-velocity coupling and examine various methods of discretizing each parameter, such as pressure, velocities, and all scalar quantities.